Okay, welcome everyone. All the ones that are left. Any insights as to where the rest of the class is?
Probably trying to do the lab, I guess.
I think some people are working on the VVV project as well. For
yeah.
The web.
Oh guys, you really get your priorities straight here, right? So which one of this course is the most important one this semester for you guys?
Graphics.
Yep.
That's correct. Okay, next most important one.
OS.
Wrong answer. Wrong answer.
Yeah, probably actually one for
So anyway, anyway, it's all screened anyway for the ones that are not there, and you should be the last one to be punished, of course, because you actually showed up. So thank you very much. Right. So one of the things that we haven't talked about, and I think we should talk about it, are build tools, right? So any clue what build tools are? Anyone? Anywhere? Yep, please.
The kind of tools for like building your project and making sure dependencies are all set up.
Cool. Yeah. So what's an example of those tools?
Gradle?
Yeah, of course. Why do you point to Gradle?
Well, I think Gradle has a lot of relevance in this course.
Yeah. So is the mobile course the only course using build tools, most likely?
Probably not.
Probably not, right? Probably not. So there's more out there. But you're right, Gradle is of course one of them. And, it's intimately tied to Android Studio and therefore has strong relevance for this course, right? But the idea is really to get the message across. And really, why do we use build tools? Well, you know, the reasons are seemingly obvious, actually, to manage dependencies, you know, and ensure the workflow, and also particularly to integrate larger projects, right? So especially if you have third-party libraries and so on that potentially need to be built as well. Well, you know, you want to do that somehow coherently in a single go. And in fact, in the given the recent focus on continuous development as one of the ways of, you know, doing modern software development, it becomes even more important to have tools that actually facilitate this, you know, starting basically from sources, compiling them, integrating them, and linking them the respective associated libraries and so on, you know, packaging, deploying, and so on, and even this, testing, for example, automatically across a infrastructure allows you to do that. So it becomes quite important to have solid build tools. None the least, it's not only that one, but also what becomes increasingly more important. The more complexity you have, the more reporting you need as well. Did a build work out? It didn't work out. Why didn't it work out? And things like that, right? So, or levels of compliance, reporting levels of test coverage, and things like that. So it's quite a bit of infrastructure that goes into that one. And do you have any course that talks about those explicitly? Build tools? Reflect. Not really? Good. So all the more reason in doing it here a bit more extensively, else I would kind of cut short. But I think it's still relevant to kind of cover that. So primarily it's really about automation, right? So it's about integrating the entire workflow. Also dealing with different platforms, right? So you can easily buy a switch, or perhaps completely automated. You can accommodate releases for different platforms, being Mac, Linux, or Windows, of course. And of course also perhaps target different users or user groups, for example, localized versions of a given app and so on, just managed by the build tool as opposed to, meaning by configuration as opposed to by the developer itself. And what's the general build process of those tools, since some of you are acquainted with them? What are the intuitive steps that we probably need to have as part of a build process? Kind of bring together your perhaps memories from application development. I think I talk about it there. But also perhaps think a bit like a compiler as well. Perhaps that helps.
What was the question again?
What are the stages or steps involved in building software?
Planning.
Well, the stuff that software can do for you. The planning is usually something that you do for the software.
I mean, just from the tiny bit I know, there's like a compiling and like a linking stuff.
For example, yep, cool. Yep, that's right. And then?
I mean,
well, you have to include external header files files, and you have to also include like libraries and maybe set preprocessor declarations.
Yeah.
If you have access to the source code, you can build the actual third-party libraries. Some people don't. Some of them obviously aren't open source.
Sometimes you're limited, of course, yes. But what's also very important if you use, let's say, open source solutions, or even closed source solutions, what's also very important to think about when you're using both your own code but also external code. What kind of functionality do you also want to do every time you want to release something? What are we aiming at highly automating? And we see that, for example, most of you have set in clouds, so we used sometimes even built in the programming languages already. Please.
Testing?
That's right. So testing is intimately tied into the whole deployment or building process in the widest sense. So if tests exist for whatever reason, run them as well for me automatically. Even though it's repeatedly, seemingly repeated, but tests are the best way of figuring out if something goes sideways, right? Particularly on a semantic level, right? So it's quite important. So so that's few ones, right? So basically development, the assembling of different resources, external and internal. Of course also the deployment, right? So perhaps even deployed down to the release side or whatever else, or uploaded to web service or or Play Store or the like. However it's actually disseminated. And then integration, and that's Ganze, this whole process is basically just done iteratively, right? So you do it repeatedly until, it actually works, hopefully, or not, right? Sometimes automated. But this is just a subset of the different build stages of the process. You will see much more complex life cycles in a second that we talk about. So, yep.
Something funny about the deploying thing.
Yeah.
There was a game studio where an employer sort of went rogue and he tried to deploy his own the things that he had added to the code, and they managed to detect it before it was actually deployed. So it's actually quite an interesting thing.
Right.
About the deployment, because to make sure that when someone pushes something, the entire team kind of knows what it's about.
Right. Cool. Yeah, I mean, definitely in the context of continuous integration, you need to have a very rigid and strict monitoring, because you're trying to automate as much as possible. More importantly is that you want to assume that everything works fine, right? Because if we don't get notified, we often make the assumption that everything works well, but that may not necessarily be the case, right? So then it's very important, especially in those exceptional cases where individuals actually have input or influence in the...
I had malicious intent, I think.
Okay, that's even worse, right? Well, but this is usually done by doing code reviews and signing of commits, for example, right? So I mean, it should be relatively hard to actually add code into a code base that is not reviewed by a third party. So I think it sounds more like an organizational requirement to think about it, right? So in order to accept pull requests, for example, into a code base. But interesting problem. I mean, if you have a concrete or example or want to share that, that's more than welcome, right? Also beyond this session. Bit of a story. Usually sometimes works better. A story. Here's history. Of course, somewhat picturesque and somewhat humoresque in a wider sense. But the tool that all of you know is Make, right? Because that's the foundation of how to initiate actually compilation in C++, as you know it, and which you were probably using quite a bit in your first year, right? So individual stages. And that's pretty much the tool everything kind of started with. I mean, at least talking about higher level programming languages in the first place. And also if you download it, for example, like in the 90s and 2000s from SourceVerge at that time. Does anyone know SourceVerge? Everyone knows SourceVerge? Who knows SourceVerge?
SourceForge?
Yeah? Oh, sorry, Forge. Yeah? Okay, 1, 2 people. What was that thing? Oh, what is that thing?
It's just like a place you can code. It's like a code repository, basically. You can put projects on it.
Exactly. So basically a predecessor of GitHub de facto, right? So when GitHub got active, they actually figured out, cool, we can actually build communities and people can fork stuff and they can interact talk about code and so on. SourceVerge is pretty much the predecessor. You basically upload your code. You have some crude discussion forums that no one used, and there was no way of actually linking stuff meaningfully other than categorizing by tags. And they usually supported CVS and SVN. I think nowadays also Git and so on, but of course the trend, has left. So they were kind of the predecessor. And when you would download stuff at that time, it was usually along the lines that you basically download something, have a makefile in there, or some shell script that generates a makefile, and then you run make and hopefully it works on your machine, right? So it was roughly a pathway. So of course this has moved since for multiple reasons. Of course, new programming languages were coming up or becoming more prominent, particularly Java, for two reasons. One of them, of course, that they were gearing towards platform independence, but also large-scale systems and integration of in large-scale systems, as opposed to just using C++, which the management of which becomes challenging at larger scales, and alternative languages such as Ruby and whatever else was out there, right? So they, of course, had their own ideas of how to integrate, especially external dependencies, and how to deal with the build process. So following make that you kind of know, and that's kind of localized and very focused, well, end came about, end, right? So Apache end. Did anyone come across this one or need to run it at some stage for some reason?
Come across it, but
yeah. So basically, it's very characteristic if you have a repository and you find a build.xml file in there. That is an end build configuration, basically, where you can just run end with the given target. We'll talk about this in a second. And then basically builds according to the specification. So and of course, also being a child of the 90s, was really big on XML. That was pretty hot at that time, right? To describe everything in in a human readable format and generically. This one doesn't work. Those ones work. Yeah, whatever. We'll come back eventually, hopefully. So in a human readable language and so on, and to make it interpretable. And there were, of course, other variants that people said, yeah, no, I actually don't want XML. So coming up with other derivatives and operating system more independent solutions as well. Whereas end, I think, operates pretty much on any operating system as long as you run Java, of course, because it's Java-based itself. So yeah, so after end, there of course were further splits, kind of forks, but derivatives of this one based on programming languages, but also based on the approach that end actually took. You'll see it in a second. I'll show you a bit of code later just to get an appreciation of what you deal with. And that's actually quite a bit of work actually to specify something in AND, but it's kind of rock solid when you execute it. And there were different pathways of making it a bit more flexible, like Ivy, for example, kind of declarative pathway, or working with integration, actually using programming languages for the specification of the build environment. So it was Gantt was the first one doing this. I can recall, and it's just basically a specification language in XML. But most importantly and most influentially was basically the introduction of Maven. Yeah, so that has become the next standard following that one pretty much. Was slightly different in that it actually introduced a bit more of a standardized life cycle, but we get to that in a second. So, and of course in succession it ended up being Gradle, the stuff we're using now, but I think it's still worthwhile getting an appreciation of what happened before that, before we see more how it works under the hood. And this is kind of what you get when you get a end file, right? The build XML, for example. So you see it's basically a project, right? The outer tag there is basically a project framing individual properties and targets. So there were two components. One of them is properties. That's basically just fields or values, that you can actually use in the remainder of the code, and targets, which contain the tasks that are done to reach a certain target. So if you think about a progression of, for example, building something and deploying something, you can specify those individual stages, if you like, as targets, right? So now you can specify, well, if you want to compile something, then you need to satisfy all preceding targets and the associated tasks in order to compile the code. In this example here, if you were to say and then with the target in it, with the target compile down here, so you have properties, you have targets, it would basically ensure that the code within the target compile section here is executed, but since it depends on init, it would previously execute the init target as well. So you can basically stage targets and link them to each other. So that would their way of doing sort of dependency management by thinking about it different basically stages and linking them dynamically, or chaining the targets rather, doing this in the attributes of the corresponding tag. So that's basically how it works, right? And internally you see that there's some sort of, they call them tasks in end. One of them is called mkdir, for example, here. The other one is you call it javac. So they're built into end itself. In this particular case, mkdir, what does that do? Linux people? Exactly, right? So it's direct representation of the Unix command mkdir, make directory, and javac is basically whatever here. Here's exactly, right? Take the stuff from that source directory, compile it, and put the classes into the destination directory there, right? So those specifications are specific to the tasks that you're dealing with, and it will only be tasks that are supported by end. But of course, you can write your own ones and extend it. But you see how it works. Basically, you specify everything in this very way that you have basically properties that you can use. In this case, for example, the source and target directories are properties of the project, so meaning can be easily reused and modified across different targets. And targets themselves contain or link to dependencies, as well as have a contained task inside, right? So that's how you build it. And you can build reasonably complex control flow. Sorry, the color choice is a bit weird, but it actually is a very nice visualization of the complexity you can actually model there. So you can actually model branches without any problem if you see the nesting characteristics. So you have different targets. In this case, one target is called nested if, the other one is called then. There is another target called inner then, inner else, and another one else. And by chaining them using the dependency relationship, you can kind of model this kind of structure, right? So so basically by running the target nested if, you would by specification basically perform an AND call on the targets then and on the target else basically, and those in turn would rely on the property condition which is specified in the target's nested if to decide whether they actually execute selected branches within the contained targets, right? So that's the rough idea here of that approach, right? So relatively straightforward, leaves everything up to you pretty much, right? So you kind of need to model that whole process yourself. What's your, looking at it just crudely right now, what's your impression?
Seems complex.
Seems complex? Why complex?
Mostly because I'm familiar with working with it.
Right. Well, it's a bit of a both, right? It's XML in the end, so you kind of have a lot to type and so on. But hang on. Yeah, that's fundamentally what you get. But if you look at the built-in tasks, you can write your own, of course. But you see what you can actually do with it. So just getting appreciation how powerful the tool actually is. So you see a lot of commands that you know from the Unix environment, for example, create something, delete something, copy something, dealing with CVS. What the heck is CVS? I just mentioned before. CVS, not CSV. No. Kind of the first versioning system that we ever had to deal with, right? CVS, and then we had SVN, and then finally we ended up Git. Similar here, the build tool progression is also kind of similar, end first and then so on. But you see the support for that kind of stuff. Deleting directories, accessing directory names, echoing stuff, executing stuff, so you can actually natively run something on the command line, zipping, unzipping, host information, and so on, right? A lot of Java-specific stuff, of course. But this is basically a built-in task that you could use. So basically, you can model any sort of file-level operation that you need to perform using that kind of task set and then nesting them in different targets, right? Kind of makes sense? Everyone somewhat on board? Relatively straightforward idea, right? So that was that one. But it allows for reasonably sophisticated setups across the file system as opposed to, for example, make files, which are really specifically focused on your project and very much on your and programming language centric anyway. This one kind of Java centric, but you could app use it for something, for other things as well. For example, you could just, of course, manipulate the file system and simply call different compiler using the exec task, right? So you say exec and execute an executable, which could very well be GCC or whatever else, right? Even though it's not a first order citizen of the task set that's built into ANS. Anyway, so that was that one, right? So we have XML. We can specify the whole execution pathway on our own using that, quite straightforward. And following this one basically was Maven, right? So it became the default build system for most Java applications. How do you know that you have a repository that's to be built with Maven? Anyone? Did anyone see? No? Yes, no. Did anyone see POM files in any repositories before? POM? POM? No? pom.xml indicates that it's actually Maven, not Maven, build specifications that are to be run. I'll show you in a bit more. So, learning, of course, any tool that you develop needs to benefit or learns from previous tools and actually refines them. So we have an element of evolution there. And one of the changes there that was related to the introduction of Maven is, well, you know, they thought, okay, even though End is powerful and you can do a lot of different stuff, you can model process flow and so on, one of the challenges is it's really hard for people that are comfortable with Maven to read other people's Maven code. Right? Because it's really up to you to structure targets, to define targets, to nest them, and all that kind of stuff. There's actually quite a few primitives to build complex files, but when it comes to reading them, it becomes incredibly complex. So what did the Maven people think? Well, you know, let's standardize the lifecycle, right? Instead of figuring out different targets and figure out how people change those targets to make dependencies, let's just assume that any piece of code that we write follows those basic steps as part of the building process, right? We're validating that the project is correct, that everything is where it's supposed to be, or necessary information. Did we provide, for example, environmental parameters that we need to locally provide before we're building something? Then we have the compilation stage. Does it work out, or does it fail? Then is there a test on the compiled source code? And is does it actually work with the testing frameworks and things like this? Package the whole thing, right? So, for example, in Java world, that would mean combining the class files into jar files, Java archives that are executable, for example. Verify that whole thing again, of course, now with integration texts, possibly. For example, that bring in other, link it to other projects and so on. And followed, of course, by the installation into a, for example, or deployment, installation or deployment in the corresponding environments. Installation if it's just locally, deployment if you want to provide to third parties. So that's basically the rough idea. Was there any comment? If you have any questions, interrupt me, right? So perhaps you have some experience or questions regarding the individual stages, right? So and that was basically the idea. So the fundamental approach was, let's simplify the whole thing by using the principle of convention over configuration. So we assume certain standards in the execution lifecycle, and the one I showed you is the short one. The longer one looks a bit more like this. So there's a lot more steps in between that actually relate to generate sources, process sources, generate resources, process the resources, then compile the whole stuff, and so on, right? So a lot of intermediary steps that come into play if you want to exploit the full life cycle. But it basically allowed you to just say, well, I want to specify the phase compile here, and you can assume that everything, if you, for example, have generate sources or initialize as part of some of your phases in your build file specifications, they will automatically run. You don't need to specify dependencies anymore. And if you are comfortable and know about Maven and you know about the lifecycle, it's a lot easier to read another person's specification, because you kind of know in which execution order things are actually going to happen, as opposed to modeling the nested target dependencies manually, right? So that was one of the key motivations. Also, for example, a very nice one is that you can assume that makes it very easy. If you want to clean your build directory, for example, you can just call Maven clean, right? So that's really nice, because it's not, you don't need to figure out which target is responsible for deleting or cleaning up the repository for building. You basically know it will be cleaned by convention, right? So, and that really makes it easy. And even if you don't know a library, you're just downloading it and you want to compile it, you can just say Maven compile, and it will actually ideally, compile without you thinking about it deeply. Whereas in End, you would need to at least know the targets that are available. So you need to inspect the file to some extent. So it makes it slightly bit more yeah, slightly more effortful, I guess. So you know, in ideal case, you just say mvn deploy, and it should execute all the different stages of the lifecycle process and deploy whatever you want to do. So kind of straightforward. So how did they do it? Well, what they do is now was slightly different. Especially they wanted to support nested projects, which you can do, of course, kind of model in End as well, but here's an explicit part of the specification. So it's again XML, of course. What else? We have the different lifecycle phases in which order they're executed, so you don't need to model the dependencies. And you have a hierarchical organization of so-called POM files. POM files, POM stands for Project Object Model, specific to Maven, of course, right? And then you have kind of a super POM, which has like the general setup, which is system-wide valid. And then for each of the nested libraries, or source libraries, if you like, they can have their own POM files. And basically, it means that they can override the global POM specifications if they're necessary. For example, changing, you know, I don't know, a property, for example, for default language to be compiled in or whatever else. And of course, extended also with specific instructions that are relevant for the individual lifecycle phases that are not captured in this kind of super POM thing there. So, and basically, by a combination of this global POM plus the specific POMs, you get the so-called effective POM, the one that is actually executed on your particular, you know, branch of your project you want to build or whatever else, right? So that's the rough idea there. Quite relatively straightforward, I guess. Well, at least conceptually. In practice, of course, it always bears challenges. Otherwise, we would still be working with it on a daily basis. Just to give you a very brief appreciation. So, older library I wrote myself some time ago, but so basically here's a library. As long as you commit to certain structural characteristics, one thing that I probably should have mentioned before that. Where is it? One thing I should have mentioned before that there are certain assumptions about, that along with the convention-based approach, come assumptions about the structure, the folder structure that you actually model your stuff in. So I'll just show it here in advance. That applies the same way for Gradle later on, but basically you have a project layout that is in the following. You have source, you have main, you have test, you have then a programming language-specific subfolder, in this case Java, and associated resources. So that's part of the convention that you lay out your repository in that very same way, right? So you need to follow, of course, the conventions, both in terms of the build model, but also in terms of the layout of the data sources to automate things. And if you really do that, and that's precisely the example here, so we have a source directory and it has exactly the characteristics. We have main and test branch and whatever else. And if you do that, things can actually get incredibly simple. You just say, well, you know, this is how I name this whole artifact right now. These are properties of what I want to, the Java version I want to compile it in, so 1.8 in this particular example, right? So, and the character set encoding of the files, and certain dependencies, yeah, please. If you run the tests, here, this is the JUnit version you're supposed to use, right? You guys know JUnit, or unit testing tool for Java specific, also in Android. We'll cover that as well at some stage. Just want to give you appreciation. That's how simple it gets, right? You don't need to think about the targets anymore in the chaining. You just say, that's the thing I'm doing, some parameters for compilation, and for testing, use that thing, right? So as long as you stick to the those conventions, it can stay remarkably simple, actually. That's the fundamental assumption here. Here's what I want. That's the slide I actually want to show. So basically, there are certain assumptions about the folder layout that you have, right? You have the main folders you have the testing folders. If you, for example, have web apps that you're having that you want to deploy, you need to put them in a folder called web app, right? Subfolder called web app. So really rigid in that respect. Integration tests are to be managed here, and so on, the sites and readmes and so on. So basically, everything can be automated in the deployment, and that makes it just very simple, similar to what I just showed you before. Quite straightforward. In addition to that, something that's in Maven that's actually cool is the ability to, source software remotely. Similar to what you know from Linux or Ubuntu in particular, you have the idea that we have repositories, right? That we can source them using apt-get in particular. Does anyone recall? Yes, distribution repositories, right? Specific to Ubuntu or Debian. And similarly here. So Ant doesn't have that infrastructure, but Maven does. So basically they have a setup for packages that are compiled and deployed, or where sources are available that are accessible and basically easily integratable into your project. I'll just show you how that looks like in practice. So basically you have the MVN repository and you just say what you actually want. An example could be see if we find that thing. Yeah, the Apache Commons IO, of course, some sort of dependency, right? And you find basically where it's provided, where it's used, and so on, and which repository it's actually available in, and which version it's available in as well. So you can click on that version, and then you find down here, cool. If you're running Maven and you want to include it as a dependency into your project, similar to what I showed you before here, dependency for JUnit, you basically just copy-paste that snippet here, and it will automatically download the dependency when it needs it, right, from the Maven repository. So quite cool. You don't need to manually figure out the folders where you put that stuff in. You just combine all the different kind of dependencies that are uploaded available in Maven. And that was a big move because it changed the game in the sense you don't need to worry about managing dependencies locally anymore, not put binaries into repos if they're, for example, not openly available as source code. Don't necessarily need to deal with the trickiness of their compilation because it's all tested and managed here. And of course, if there are issues, they are much faster figured out here in the centralized community than by you individually, right? So that's basically the rough idea. And as you see, this whole concept is still existing and it will remain relevant. So it's worthwhile keep an eye on it because the Maven repository infrastructure is also, of course, used by Gradle itself. The commands are slightly different, but fundamentally the same thing. SBT, it's the Scala build tool. If you deal with Scala, for example, that's the kind of command. Ivy grape, lining in, which is for closure. That's an interesting beast, and basically other tools as well. So the kind of Maven have kind of made a central move here and has become a representative tool and protocol and infrastructure for any of those build tools. And there's various ways of having Maven repositories. You can have them locally on your machine, literally locally. They can also be considered remotes. That means organizational network. For example, you have packages that you want to manage centrally to some extent, but please within inside the confines of your organization, so you don't want to make them public. And then, of course, the central one, which is entirely public, right? Available to community. So that's the third variant of repositories that are available. There are various ones that are provided, but Maven Central is generally the place to go to if you're looking for packages that you want to use in your files. So yeah, how do you run Maven? So with all this in mind, how do you basically run Maven? Again, you just need to know about the structure. You need to know about the different lifecycle stages. And then it becomes incredibly easy. Like running Maven install, you know everything up to lifecycle point install is run in Maven. That was validation, compile, test, and so on, some of the other ones. And you know it will actually end up there. You just need to know the specs to some extent. And here, for example, you want to do a clean install, you would just run mvn clean, meaning it does cleaning first, and then mvn install, meaning run mvn to install afterwards. So you can chain basically those target executions. So that's a classic one. MVN clean install, if you see that somewhere, it basically means those two things. Clean up, so we have a clean build environment, and then install the whole thing, so it actually runs. Right? So quite a no-brainer, quite straightforward to do if you are comfortable with this. Cool. What are the challenges? Well, XML has its challenges on its own, but that's not the key thing. What is sometimes tough is actually to keep track, especially for larger projects, of the effective POM. Right? Because you have the super POM in the root and so on, and then individual branches with their own ones. So what's effectively actually valid? Which values are actually executed? So that's sometimes a bit tricky. There are, of course, tools supporting that, but nevertheless, needs to be kind of figured out. Maven itself is kind of Java-centric, but Java is one of the most important enterprise software development environments, and there's huge community and large number of libraries, third-party libraries that are available. In particular, and not the least, I mean, one of the aspects that keeps it alive, for example, is also Android, of course, which thrives on it. So Maven is quite verbose in the execution, and probably the more annoying bit, or let's say the last annoying bit, is it doesn't retain compilation state, which sucks a bit, because if you think about this long lifecycle process, you kind of, if you want to rerun it again, it does everything from scratch. It doesn't keep track where it ended up or where it failed, and basically just backtracks and goes to the previous stage and continues from there on. Nope, it goes all the way back and starts it from scratch. For our little projects that we do here and there, it doesn't really matter, but for bigger picture, like enterprise level projects that integrate other resources, it becomes quite expensive and tedious, and takes quite some time to actually do stuff. A thing that's slightly more annoying, at least that's my experience, is you kind of need, it's super extensible plugins, but as soon as you're off the beaten track, and off the beaten track basically means that you don't follow the conventions to some extent, or need to do manipulation on your source code or whatever else, it becomes incredibly tedious. You need to use quite straightforward, you need to use plugins to do everything. And I'll show you an example for this. Similar, no, I'm not showing you that one, that's too messy. Cool. So, similar as before, right? You're building something, slightly different library, doesn't matter. It has, you specify the parent pom file. I'm not going to super pom this, just the environmental setup. Perhaps we can look in it later, but that's not the key point here. So you point to the parent pom file, then you say what this thing is actually about that you're building right now. In this case, oh yeah, cool, that will be a library, dbscan library, a certain version, and it's packaged as a jar file, and it has certain dependencies it relies on. Cool, so far so good. Quite straightforward, right? No magic there. But then I had a slight issue that I needed to modify source files for a slightly different version of that runtime environment. So it's kind of a simulation tool, and there was a version change. There were some syntactic changes. And the only thing I actually needed to do was basically to replace 1 or 2 lines of code in my code, because the import path has changed, basically. And that's what happened. That's basically the same library. So suddenly, I needed plugins for everything. That was a plugin that was responsible for copying files, so creating temporary folders and copying files to it. Of course, potentially for restoring the file itself, but also for replacing code in the files. I actually need to have a separate plugin, which is the Maven Replacer plugin, for example, which you need to specify when it actually is supposed to be running during the process sources file. Suddenly you sneak in this replace functionality, and you say, well, do the following to my files. This is what you look for, this is what you replace it with. But if you see, compared to the very short file of basically 3 main elements, suddenly it becomes like that. It becomes incredibly tedious. And that's it kind of would be kind of a one-liner in Bash, basically, doing that replacement quite straightforward. So it becomes very, very tedious. As soon as you're off the beaten track, you need to use plugins, and then it becomes, slightly more verbose, if you like. So that's just a bit of a take on that one. So far so good, also worthwhile knowing about. And then, of course, Gradle integrating all of those aspects. But before we talk a bit more Gradle, and I see you kind of falling asleep, that's sensible. I give you 10 minutes break, I guess, and then we continue there, and I'll wrap it up and hopefully close a bit early today. So.